have a big goal for this episode of Chalk Talk. Are you prepared? We're going to electrify the world. I know. What are we doing sitting here? We need to get going. But where do we start? With energy storage and sector coupling. That's where. Hi, I'm Amelia Dalton, host of Chalk Talk. Climate change is making better energy storage more important than ever before. In this episode of Chalk Talk, Dr. Rüdiger Meyer from Phoenix Contact joins me to discuss the what, where, and how of energy storage systems. We take a closer look at the structure and components included in typical energy storage systems and investigate the role that connectors play in successful energy storage systems. And before we get started, don't forget to click that link. There you can find even more information about this topic from Phoenix Contact. Hi, Rudy. Thank you so much for joining me.
Amelia, thank you for giving me the chance.
Absolutely. Okay, so we're talking about connectors and energy storage today. But before we get started, the need for better energy storage is driven by climate change, right, Rudy?
This is absolutely right. And I want to go to the first slide of my presentation. I think every one of us is aware that climate change becomes visible even in our industrialized countries, in our home countries. And the next slides will show some examples: flooding in towns in Germany, drying up woods and forests, dried out rivers, and melting ice. I think this is more or less obvious for everyone now.
I think you're right. Now, Rudy, what is Phoenix Contact's approach to climate change in general?
Our management has analyzed the Sustainable Development Goals of the United Nations, the so-called SDGs, and found that more or less half of them are achievable by using technology. And thus we have decided to define our decade goal to be enabling the all-electric society. And enabling the all-electric society in first order needs sector coupling, so coupling the different sectors of our economy and society.
Now, electrification can be found in almost all areas of our society these days, right?
That's absolutely right. We at Phoenix, we talk about the different sectors in terms of smart industry, smart buildings, smart mobility, the smart energy, mainly renewable energies, wind and solar and others, and of course, the link between all this, the smart infrastructure. Batteries, energy storage are more or less everywhere.
So let's talk more. How does energy storage come into play here?
Energy storage is more or less the key, because if you have volatile energy producing units like the renewable energies, then you not always have energy at the time that you need it, that the consumers need the energy. That can be solved in parts by using smart systems, smart infrastructure in terms of data communication. But however, you always need to time shift this energy that is provided by the renewables. And for that, you need energy storage, because they can really store this provided energy, although that is also important. But when talking about stationary energy storage, we see different sizes and thus can differentiate between the different types. The smallest ones are the residential storage systems that are often used in private households to really cover the PV systems and even provide energy for private charging stations for the e-mobile. Then we do have the commercial storage systems, a little bit larger size. We are talking about capacities in the range of several 10 kilowatt hours. And again, a little bit larger, the industrial storage systems, where we really have whole rooms that are filled with storage racks. And the larger size is the utility storage system. Here we talk about containers, really placed somewhere in the field, in the green field, mainly at connecting points to the grid.
That makes sense. Now, what kind of use cases are you seeing here?
So some of them are well known, I think, by many of you. We talk about uninterruptible power supply. This is a very traditional use case for energy storage. And of course, what I mentioned before, the compensation of the renewable energies, the time shift of the energy. But we can also use energy storage systems for grid stability, for stabilizing the public grid, because they are very fast in reaction. We can use these batteries for peak shaving, to really cut the demand peaks by providing the energy from the battery and thus not to load the public grid. Then we have the black start use case. When the grid is really shut down due to an accident or whatever, it has to be restarted, and there we need large amounts of energy in a very short term. And last but not least, we have the so-called islanded grid. That is, for example, in rural areas where no public grid is available. Energy storage systems can be used to provide energy for small areas. But this is also some application for industrial needs, for example, mining, because mining in many cases is also an off-grid application, which is nowadays fired by diesel engines, and that could be supported at least or even exchanged by energy storage systems.
That makes sense. Now, Rudy, can we dig into the details of an ESS?
Yes, of course. I always like to compare an energy storage systems with the human body. We see it here in this slide. A human body has organs, but has also nerves and veins and senses. And the same is more or less in energy storage systems. We have signals, which is comparable to the sensors, which are transmitting temperatures or smoke events or voltages or currents. These are sensors. Then we have data streams, information that has to be transmitted. This is very comparable to our nerves in the human body. And last but not least, we also have the power transmission. That is the main use case of the energy storage. And this can be compared to the veins of the human body.
Huh, interesting. Now, Rudy, what kind of errors are you seeing in these kind of electrical interfaces?
Really a few possible. And of course, if these nerves or the veins or the sensors do not work properly, then the whole body is not working properly. Maybe in the worst case is breaking down. And the same for energy storage systems. Nowadays, in many cases, power connections are realized by screws. And if you do not supervise the torque of the screws properly, or if there are vibrations or material fluctuations that are loosening the screws, the contact resistance will increase. And this results in heat losses in the best case. In the worst case, in really strong overheating and fire events, which would destroy the energy storage system. And I have done a kind of loss calculation with some certain assumptions shown on this slide here, with a standard battery module of 5 kilowatt hours of capacity, 48 volt module voltage, 50 amps of mean module current. And I have calculated this for 5,000 full cycles, which more or less relates to the lifetime of such a battery module. And then if we look at only the two battery poles shown here on this picture on the right-hand side, they have always a kind of transition resistance, which is in the normal case around about 1 milliohm. And then we have energy losses of around about 100 kilowatt hours over the whole lifetime, only at this one single battery module. And there are a lot of them inside an energy storage system. If this resistance increases a little bit, which I would call an undetected failure because it's only get a little bit warmer, it doesn't glue or melt or whatever, I have calculated this case for 30 milliohm. Then we talk about energy loss of more than 3,000 kilowatt hours, which corresponds to the mean electrical energy consumption of a family of 3 in an industrial country like Germany, for example, or the US. And I think this is really amazing because at the end, it's money of the end consumer of this electrical system.
So, Rudy, there can also be a failure at the sensor connection level as well?
Absolutely, yes. If you look at this picture that I show here, you see a sensor which is in many cases directly soldered into the PCB, the wire ends. And in this case, we can have, for example, cold solder joints or poorly prepared wires, which would result in voltage drop at these contacts. And that means that the sensor is measuring the wrong signal, and that would end up in, for example, in case of voltage failures, in loss of capacity of the battery, or in case of current failures, in an early aging of the battery because we would charge and discharge with, for example, a too high or too low current.
Okay, so Rudy, what other kinds of failures are you seeing?
Yeah, at the beginning, I've mentioned the 3 different signals, power, signal, and data, and now data is left. You see it on this slide here. We have data, of course, in most cases connected via connectors, but even connectors can have differences in terms of tolerances. We can have low quality of the contact surfaces. We can have poorly prepared wires as well. That would result in the best case low data rates, low transmission rates, maybe even in failure in the data transmission, but that would mean that we would have some kind of frequent system malfunctions, maybe even system failures, or in the worst case, damaged hardware. And finally, again, cost.
Sure. So, what are we looking at when it comes to the structure of these energy storage systems?
Yeah, let me come back to the picture I showed before, the container. And I would like to go into a little bit more detail at 5 different levels of this energy storage system, starting with the battery module. This is the lowest level, even in terms of complexity. Here we do have different requirements in terms of connectivity for power from cell to cell, for charging and discharging the cells, and even for balancing single cells. We have signal wires for controlling the temperatures, for example, or even for controlling a fan that may be required for this kind of battery. And of course, we have communication. We have data wires which collect and transmit the respective information to the next level.
So, what does Phoenix Contact have to offer when it comes to battery modules?
I have chosen some exemplary portfolio for this battery module. Of course, there is much more that can be used and that we offer, but I, in this case, want to focus on PCB connectivity because inside these battery modules, there are a lot of PCBs that need connections. At Phoenix, we have a lot of different possibilities to connect signal, data, and power to the PCB. For example, we have PCB connectors and PCB terminals. We do have different ways to connect the wire, crimp, push-in, IDC technologies, and others. We do have, as shown in the upper right picture, elements without any isolation requirement, which is, of course, the most cost-effective one. We do have data connectivities for the PCB level, and we do have very attractive and innovative ways to directly connect the wire to the PCB without any wire pretreatment. This is the so-called IDC technology, isolation displacement connection. Having said this, I would like to switch to the next level of energy storage. That would be rack battery management system. So in every battery rack, we have one insert that is used to really control this single rack. And you see it on the slide. We have, again, a lot of PCB connectivity for power. We have to charge and discharge the complete rack. We have to transmit the power to a kind of collecting line behind the rack. We have signals that have to be connected, control signals and sensor signals. And of course, we have data communication between this management system and the subsequent battery modules, but also with the upper level system management. That will be the next stage. And on the PCB as well as on the device level, that means in the device housing to really connect the outside, we have different ways to mark the respective PCB terminals, for example, by color coding, by printing, to make it really safe in terms of installation. We have shielded and unshielded PCB connectivity for data, always a question of requirement and thus of cost. Very innovative is our board-to-board series, connection between 2 PCB boards, very attractive and convenient for the operator and for the installer, but also designed for high data rates up to 16 gigabit. And of course, we have a lot of data connectivity for the device itself, for the outer connection, for the field connectivity. And in this case, I have chosen one example, a circular connector with a specific D and X coding, which is even standardized so that it really fits to every respective counterpart of connector from different competitors as well. The next stage in the energy storage system that you can hear on this slide is the complete rack cabling. So this is the wiring of the container inside. Here we again have power connectivity, we have signals, we have data like shown on this slide. When talking about Phoenix Contact portfolio, I have chosen in this case device connectivity in terms of cables and different ways to make this outer connection, starting on the upper left with our so-called battery pole connectors, which are available as standalone device or standalone component, as well as pre-configured or pre-assembled harness. And alternative is our so-called busbar connector. If you want to really have a very safe and convenient way to connect your rack inserts and don't want to do the cabling on the front side, you can use this rear side wiring directly connecting to copper busbars. And there is really no time required for cabling itself because at the moment when you slide in your battery module, you have connected it on the rear. That is the most convenient way to do this. These types of power connectors are both designed for up to 1500 watt DC and up to 350 amps of current. And also we have solution for data as well as for signal lines. We have different patch cords for data connectivity with the standard RJ45 interface, with the new SPE interface for USB, for HDMI, whatever you require. And I think specifically for energy storage, RJ45 is common, but SPE could be kind of new standard because it's much smaller and still fulfills all the requirements of this energy storage system. So we now have talked about the racks, but there are several racks to be combined and to be controlled. And for that, usually in this container, you find a kind of cabinet. And inside the cabinet, we have the system management that has the role to manage all the auxiliary systems, to collect the complete current, to communicate with the outer world. And here we again have power, signal, and data connectivity. We have the interface, the power interface to the rack. We have the power interface to the external grid. We again have control and sensor signals, and of course, data communication, which is required at every level of this energy storage systems. Here I have selected mainly connectivity solutions and even electronic housing solutions for DIN rail applications, as well as for cabinet wall mount interconnections and interfaces, starting with DIN rail adapter for RJ45 cabling that also can be used for fiber optic cabling on the upper left side. Lower left side, you see an electronic housing designed for DIN rail applications that the customers can use for really implementing their own electronic hardware. These housings have a kind of modular approach, and the customer can really adapt it to its requirements and needs. If there are data and power to be connected through the cabinet walls, then we again have a large range of circular connectors. In this case, what I've shown here, the larger range, 17 to M58, which really has the ability to transmit power and signal and data even in a kind of hybrid approach to only use one connector for all three different signals. And for large power applications, we do have the so-called feed-through terminals, which can carry currents up to 309 amps at high voltages with different possibilities to connect the respective wires. Okay, and the last level of the energy storage system is to connect it with the external world, with the grid, with 3D parties that use energy storage grid service applications, for example. And also again here we do have power connectivity because we have to transmit the power into the grid or even back to the energy storage to charge it. We have control signals to connect sensors and other senses of the external world. And we again have the data communication mainly to the point of connection of the grid with the grid operator and with the third parties that I mentioned before. There is a lot of different patch cable types that we offer to the customers for the different ways of fiber optic connectivity, like SC duplex, LC duplex, ST duplex, SC quad, and E2000. Different fiber types are offered and can be used with our components. Last but not least, there's a large range of accessories in the left lower part of this slide, for example, this fiber optic transceiver to combine different signals.
Okay, Rudy, so it seems like Phoenix Contact has a lot to offer when it comes to specific application solutions.
Yeah, thank you for this question. That is right. Of course, we have a very broad portfolio of standard products, but it's always possible that our customer don't find the right component, the right solution for their application. And in this case, we offer our solution business. That means we communicate with the customer, look at their challenge and find a way how to solve it by adapting existing articles or even designing new ones by using as much as existing components as possible to make it cost effective. And you see here some examples. There are combined connector systems, see on the left, with power, signal, and data combined in one connector, a kind of hybrid approach for a very specific outline and interface. It is possible to directly integrate the connector into front plates within a molding process so that there is no mounting required at the manufacturing side of the customer. There are very customer-specific housings possible, even single parts of our components that usually are not part of our portfolio, but that can be offered if the customer is willing to design its own solution by using these parts. The process looks like shown on this slide. We have a preliminary clarification with the customer. Then we do a lot of design work and always interact with the customer, give them a feedback of interim status. At the end, it's a production-ready product that can be offered to the customer, including the logistics, so that we really have the right product at the right place where the customer needs it. And finally, we do follow up during the complete life cycle of this product so that we are on the side of our customers at every time of this product life cycle.
Excellent. Now, Rudy, as a whole, what does Phoenix Contact offer me as an engineer?
Of course, we don't only want to offer components, but we do want to be a partner of our customers, and thus we offer several services. The first one I have just described, the customer-specific solutions. Another one are a lot of different configurators for the different types of components that we deliver, for example, pre-assembled cables or housings or whatever that can be designed by the customer using these configurators. We have a sample service where the customer can order small numbers of samples for free to really check whether they fit to their applications. We offer consulting in many cases, and of course, we offer 3D data for our products and components so that the customer can use them in their respective system to implement it in their design. As you can see here on this slide, we have a portfolio of more than 100,000 innovative products. And many of these products can be used for energy storage systems. So I have talked about connectivity today, but there is much more. There are sensors, there are human-machine interfaces, there is a lot of DIN rail applications like power supplies, there are controllers, and so on and so forth. And I think and hope that our customers will find their respective solution and requirement in our portfolio and will see Phoenix Contact as a reliable partner with a broad range of solutions.
Excellent. So, Rudy, if my audience would like more information, where should they go?
I have collected my contact data on the last slide of my presentation here. You can find my direct phone numbers, you can find my email address, and of course we have a landing page for energy storage systems where you also find all these information that I have provided here on this slide, as well as the sample service, as some videos for specific components and products that would help a customer to find solutions for his requirements.
Excellent. Well, Rudy, I think that's all I have time for today. Thank you so much for joining me.
Thank you, Amelia. Have a nice day, and thank you to our customers.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Phoenix Contact. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talks section of EE Journal. You can't miss it, it's right across the top. Or check out YouTube, youtube.com/EEJournal.